Hello and welcome to the channel. I'll be explaining you this problem exponentiation, and a follow-up problem to this is exponentiation 2. Basically this is binary exponentiation question, and I'll be explaining you binary exponentiation and Fermat's-Little theorem. Okay, so the problem is your task is to efficiently calculate the value of a raised to power b modulo 10 raised to power 9 plus 7, and also 0 raised to power 0 is 1. Now, of course, and by the way, this number 10 to the power 9 plus 7 is a prime number, and it has to be a prime number. It can be any other prime number as well. But why 10 to the power 9 plus 7? It has some properties. Okay, it comes just under the nth range, maximum range, and it is a prime number. And it has to be a prime number. Why? I'll explain you later. Okay. Now, as I said, this is a binary exponentiation problem, and you will have to remember this. So now, first of all, there is an iterative method, the brute force method, where you can just multiply b times a and you'll get the answer and take a modulo. But of course, that won't work because it will give you a TLE. 10 raised to the power 9 times won't work in 1 second. Okay. And also, you have n that goes to 10 to the power 5. So let's jump to the binary exponentiation. Okay. Now, you're supposed to find this. And also, by the way, I'm really sorry for not using the tablet. I'll use that later. I don't have it right now. Okay. So, anyways, you're supposed to find this a raised to power b mod something mod. Let's call that a huge number mod. Okay. Now, as I said, the main problem is that you'll have to iterate b times, and b can be very large. So basically, you need to optimize b. So b can be written in binary forms. Let's say I'm taking an example of this problem. Okay, 25 raised to power 27. 27 can be expressed as 11011 in binary format, and that is basically when you change it to decimal format, you'll get this. So the one represents, you need to take that number multiplied by its position, right, like to the power position. For example, this one will be 2 raised to power 0, and you need to take that number. So 2 raised to power 0 is 1. This will be 2 raised to power 1, that is 2, and similarly. Okay, so on. So basically, this problem turns out to be, you need to find this, and this is far easier than finding the whole thing at once. Now, basically, this breaks down to, um, since multiplication, or I should say power, is associative in this terms. I don't think I'm using the right term, but okay, you get the point, right? It turns out to be 5 raised to power 16 into 5 raised to power 4 into some and so on, 8. Sorry. So the thing is that you'll have to find 5 raised to power 16, and while finding 5 raised to power 16, you'll find 5 raised to power 8. Basically, you'll take the square of it. And to find 5 raised to power 8, you'll have to find 5 raised to power 4. And to do so, you'll have to find 5 raised to power 2, and so on, so on, so on. So basically, you'll get a memorization type of thing going on, right? So this is far easier than, like, at max it will take you what, 32 steps, compared to n steps you're taking 32 steps. That is basically log 10 to the power 9. That gives you roughly about 32, right? And so this is far easier. And yeah, so 5 raised to the power 27 breaks down to this. And then also you'd have to do the modular arithmetic properly. Okay, and now I'll show you the code. So this is the code. I'm taking a temp equals to x because I don't want to change the variable x. That would be problematic for me. Okay, no, temp is not required. Why am I taking temp? Right, I don't think, yeah. Hmm. Now, why? So you'll have to check if the number is set or not. If it's set, then only you'll have to take that multiplicative part, right? For example, here 4 was not set. My cursor keeps on flickering for some reason whenever I use OBS. Anyways, for this to be server 4, it is not set, so I'm not taking it. You can see that here. But for the rest ones, you will have to take it. So how do you check that? Basically, you keep on changing the value of y, which is basically b, right? If the last bit is set, you'll have to take the last bit, right? That's what I'm doing. And also, you'll have to use long multiplication. And x, as I said to you that you'll have to find every uh, every value of from 2 to the power 0 to 2 to the power 16 here. So you'll have to keep on multiplying the same number repetitively. That's what I'm doing to x. And for I'm always checking for y for the last bit of y. So I'll need to divide it by 2 every single time. So the bit sets itself to right, pushes itself to right. For example, if I divide 27 by 2, this bit will be gone and you'll be left with this much. Okay, it pushes itself to right. Okay, and similarly, you'll see if the bit is set, then you take it, you multiply it to the answer. If it's not set, you just leave it. Okay, and you just return the answer. Now, this was the answer for just binary exponentiation. Now I'll explain you this other code, other problem, exponentiation 2. Now here you're supposed to find a raised to power b raised to power c modulo 10 raised to power 9 plus 7. And again, 0 raised to power 0 is 1. Then, first of all, you know how to find a raised to power b modulo something. Okay. So for this problem, the main problem here is that you've been given modulo for this whole thing, right? You're supposed you've been given the whole module thing for a raised to power b raised to power c, right? And then you need to take a modulo. But I can see that this the whole number will be a huge number for some case. But at the same time, this can also be a huge number. This can also exceed the uh, what do you call it? The range of a data type. Okay, but we've not been given any modulo number for this number. So what do we do for that? Because you're supposed to take the modulo for the whole thing, not for individuals, right? And there is no modulo arithmetic for what do you call it? Power, right? So you'll have to use the Fermat-Little theorem for this. Now, how do you do this? So by Fermat's Little theorem, anything raised to power p minus 1 is 1 modulo p. And here, a and p has to be co-primes. This is the important part. Okay, right. This is important. So now I want you to now remember the value of mod that we were given 1 raised to power 9 plus 7, right? And I told you repetitively that it was a prime number. So every prime number, any number to a prime number is a co-prime, right? That was the main, you know, reason behind taking that number, by choosing that number. That we can apply Fermat's Little theorem for that number. When we take modulo for it, we'll be able to use this theorem. So P is basically that number, right? But again, this doesn't solve anything for us right now. But we can definitely do something. Now, one thing that you need to keep in mind is that if I multiply, anything x into p minus 1 in this Fermat's Little theorem, then the result won't change. I hope this is clear. If it's not, then you can just do this, right? You can also write this a raised to the power p minus 1 into a raised to the power p minus 1 into, and so on, so on, so on. And also the modulo thing, you can take it anywhere, right? You can basically take it anywhere. And but anyways, that won't we won't require that. The whole thing till x times, okay? X times. You know the value of this. it's 1 modulo p. Similarly for this is 1 modulo p till x times. So basically 1 modulo p, sorry, into 1 modulo p into till x times, and the whole thing you can take modulo over at the whole thing as well. That won't make a difference. Yeah, like by the way, you can take modulo both sides and it won't change anything, right? For this statement as well. But again, I'm taking modulo the for the whole thing, and then you'll see that it's basically 1 modulo p. So LHS equals to RHS. Basically, that's what I'm trying to prove is that these two things is same, right? This statement is true. Now, but it's not always the case. Like if I give you a number k for some k, which can be represented as basically you have to divide it by p minus 1. Why? Because we need to use this formula somehow, right? Why are we even thinking about this formula? Is because this formula involves a modulo number and it also involves a prime number. Try to understand that. Okay. Now, um, so we are basically trying to change the what's given to us, that is a raised to power b raised to power c, to something like this format. Okay. So for some k, which can be written in terms of p minus 1 as this, r is the remainder, you can write a raised to power k as this, of course, right? And this will, when you simplify this whole term will multiply itself, right? And you know the value of this is 1. I've already proven this here. And what's we are left with this number only, right? And r is, as I already told you, k modulo p minus 1 is r. So for any number a raised to power k, the whole thing can be also be written as a raised to power k modulo p minus 1, right? So now we know, because we weren't knowing for b raised to power c, we didn't know what modulo to use. So we can write this as b raised to the power c. Basically, we can write this whole thing in terms of p minus 1. That's what I'm trying to say. Okay, as b raised to power c modulo p minus 1. Oh, okay. You might even think that how you're written, it should be b, c raised to the power something something. Um, I'm trying to write this, by the way. The k is b raised to power c. I'm sorry for that if that confused you. Okay, now, and a will become like this. Okay, sorry for that. Okay, now it's clear, I think. So basically replacing k by b raised to power c, and you'll be left with this. And you also need to take modulo. I'm taking modulo both sides. That will take you modulo the whole thing. Um, and then modulo again p. So this is basically the question. If you see, this is what we needed to find. We have found the modulo for b raised to power c, which is p minus 1, right? And okay, by the way, you might even think, okay, this is no more a prime number. I know that. We have already, this was supposed to be a prime number. P and A used to be was supposed to be co-primes, right? You can take modulo with anything, but these two numbers should be prime, A and P. And P is prime, so sorry, these two numbers should be co-prime, and P is prime, so the other number will be co-prime to it. So now I'll just show you the code. Okay, simple. Again, I'll have to explain you something. You can find this by the past thing that I just showed you, exponentiation 1, binary exponentiation. You have to take modulo with p minus 1. That's it. And then you'll have to find the same thing using a raised to power the thing that you found, the value that you found, and take modulo with. P. Okay, that's it. Okay, I'll leave the link to the code in the description. Okay, so I'll show you it works by the way. Anyways, okay then. Thank you.